Generative adversarial networks to modify existing images with new predictions. For example, we can take an image of yours truly and use a GAN to generate a prediction of what I'll look like in 20 years. In fact, this deep learning application is so good that it tricked the age detection algorithms into thinking that I was exactly 20 years older. We can also use deep learning to generate entirely new images from scratch. This deep learning algorithm learned to paint in the style of Rembrandt from looking at a large sample of Rembrandt's existing paintings. As a result, it can now create entirely new works in the style of Rembrandt. And how about these fake celebrities? Each of these images was created by a generative adversarial network. They may feel like real celebrities since the GAN was trained using more than 200,000 high-resolution images of real celebrities. However, not a single one of these synthetic celebrities is a real person. Let's watch as the GAN learns how to construct new celebrity images over time. As we can see, with each training step, the GAN gets progressively better at generating new synthetic celebrities. Finally, we're rapidly nearing a point in time where we can synthesize new images based on a description of what we want the image to look like. For example, all of these images were generated by a generative adversarial network using the descriptions above. It won't be long before we can just tell the computer what kind of image we need for our document or presentation, and it will synthesize an entirely new image to match our description. This should give you a pretty good idea of the new applications for images that deep learning will likely enable in the near future. Now let's look at deep learning applications involving audio data. With deep learning, we can map audio as an input to a wide variety of outputs. For example, we can use combinations of CNNs and RNNs to classify the source of a sound. This allows computers to recognize the song that you're listening to based on the music it's hearing. It also allows computers to recognize animals, vehicles, and environmental noises by sound alone. In addition, we can also use combinations of CNNs and RNNs to perform speech-to-text translation at near human-level accuracy. If you've noticed how much better your smartphone has gotten at interpreting your commands in the past few years, once again, you can thank deep learning for the recent improvements. We can also use combinations of CNN and RNN encoder-decoder networks to perform real-time speech translation. For example, I can speak a sentence in one language, and in near real time, the listener will hear what I said in their native language. But we can also use deep learning to generate audio as an output, given a variety of inputs. For example, using a type of deep neural network architecture known as a dilated causal convolutional neural network, we can have deep learning speech synthesis that sounds almost indistinguishable from actual human speech. Let's take a listen to the state of the art in speech synthesis at the time this course was created.
The Blue Lagoon is a 1980 American romance and adventure film directed by Randall Kleiser.
But we can also train deep learning algorithms to synthesize our own voice. For example, this is the real me, and this is a deep learning voice synthesizer trained using my voice. While it's not quite perfect yet, I'm hoping to be able to use similar technology soon to fix small errors in narration for my online courses like this one. Finally, here's an experimental application that's currently in development by Princeton University and Adobe. It allows you to feed in your audio recordings, it converts your audio into a transcript, and then it allows you to edit the text just like a text editor. Then, after you've made your changes to the text, it synthesizes new audio that sounds almost identical to your own voice. While this specific application might be a few years away yet, I think it gives you a pretty good idea of how deep learning is going to lead to entirely new applications for audio in the next few years. Now let's learn about how deep learning can be used for applications involving video. With deep learning, we can map video as an input to a variety of types of outputs. For example, many of the deep learning tasks that we previously saw applied to images, we can now perform on video in real time. This includes tasks like object detection, where we classify an object as it's moving from frame to frame, facial recognition, where we recognize a person's face in a moving video, and outcome prediction, where we analyze a few frames of video to attempt to predict what will happen next. Plus, this is also leading to entirely new applications like real-time sign language translation and computer-based lip reading. In fact, real-time sign language translation is rapidly approaching human-level proficiency, and Google's LipNet is currently better than the average human lip reader. However, even more impressive is that we can now use deep learning to generate video as an output from a variety of inputs. For example, using a combination of convolutional encoder-decoder networks, we can now teach a computer to automatically colorize black and white videos. In addition, machines are also being taught to restore old or damaged films as well. And check this out. The following 4 synthetic videos of former US President Barack Obama were created by a lip-syncing deep learning algorithm. It was trained using previous videos of him speaking and generates synthetic speaking patterns as video output. It uses only the real audio from another video that's not being shown as the input source to generate the synthetic videos.
To help families refinance their homes, to invest in things like high-tech manufacturing, clean energy, and the infrastructure that creates good new jobs.
You can see why it's so important that people understand the potential applications for deep learning before someone tries to use deep learning to deceive others for nefarious purposes. And on a lighter note, just to show off the creative potential for deep learning, this video was created by musician James Poof Roberts using Google's deep learning algorithm called Deep Dream. The deep neural network was trained to detect only dogs, so everything it sees is some kind of dog. Essentially, the algorithm is hallucinating dogs. While there currently aren't many existing applications for deep learning involving video for me to demonstrate today, I think this should give you an idea of where things are going for deep learning applications involving video in the future. Finally, let's look at other future deep learning applications beyond the basic input-to-output mappings that we've already seen. It's important to note that what we've seen so far is just the beginning of deep learning technologies. Deep learning can be applied to a variety of other inputs and produce a variety of other outputs. Plus, we can combine multiple types of inputs and produce multiple types of outputs as well. This leads to a whole new realm of possible applications for deep learning in the future. For example, self-driving cars connect a variety of sensor inputs with a set of vehicle control outputs to drive an automobile without any human intervention. This same deep learning technology can also be applied to other types of vehicles like semis, buses, boats, airplanes, and drones as well. In addition, attempts have been made to use deep learning to teach artificial bodies to walk in a simulated environment. Once you can get a virtual body to walk in a computer simulation, you're one big step closer to getting a robot to walk in the real world. In fact, some of the most impressive new technologies in the coming decade will likely be the result of creative applications of deep learning to a variety of novel inputs and outputs. Finally, while we're on the subject of potential future applications for deep learning, I want to point out that deep learning isn't the only way to solve complex problems. The robot you see here was programmed without any deep learning technology. So while deep learning may be quite powerful, it's not the only way to solve these types of complex new problems. I anticipate that we're going to see a variety of new applications for deep learning in the years to come, many of which would seem like science fiction to us today. So you should really be asking yourself, which problems could my organization solve today using these existing deep learning applications? And which problems will my organization be able to solve in the future using the next generation of deep learning technologies? In this module, first we learned about deep learning applications involving tabular data. For example, classification, regression, and clustering using tables of data. Next, we learned about applications involving textual data. For example, document classification, natural language processing, and language translation. Then we learned about applications for images. For example, image classification, image captioning, and image synthesis. Next, we learned about applications for audio. For example, speech-to-text translation, sound detection, and speech synthesis. Then we learned about applications involving video. For example, real-time object detection, automatic film colorization, and video synthesis. Finally, we learned about future applications for deep learning. For example, autonomous vehicles and robotics. In the next module, we'll learn about the impact of deep learning technologies. Hello again, and welcome back to Deep Learning the Big Picture. I'm Matthew Renzi with Pluralsight, and in this module, we'll learn about the impact of deep learning technologies. As an overview of this module, first, we'll learn about the history of deep learning and the obstacles this technology has overcome. Next, we'll learn about the trends that are currently enabling and driving the importance of deep learning. Finally, we'll look to the future to see what impact deep learning will likely have on a variety of industries over the next few years. So let's get started. The earliest neural networks, called perceptrons, date all the way back to 1957. So what changed? Why has it taken almost 60 years for us to get to deep learning? In the past, we had some machines that were capable of making rational decisions. Hello again, and welcome back to Deep Learning the Big Picture. I'm Matthew Renzi with Pluralsight, and in this module, we'll learn about the impact of deep learning technologies. As an overview of this module, the earliest neural networks, called perceptrons, date all the way back to 1957. So what changed? Why has it taken almost 60 years for us to get to deep learning? In the past, we had some machines that were capable of making rational decisions. However, they had to be explicitly programmed to make these decisions, and they could only operate successfully in very constrained environments. There was a lot of hype about what artificial intelligence would be able to accomplish. Many experts eagerly predicted that machines would soon replace all human labor, but it never happened. By the end of the 90s, machines couldn't even solve basic general-purpose tasks that even a toddler could solve. The inflated hype about the potential of artificial intelligence and subsequent disillusionment when it never happened led to what we now refer to as the AI winter. The AI winter was a period between the late 70s into the early 2000s where funding for research and startups involving artificial intelligence had almost completely dried up. However, by the mid 2000s, the AI winter ended and things began warming up again with the emergence of modern machine learning. Machine learning began to grow in popularity as companies like Google showed the software industry how machine learning could be applied to solve common business problems. However, while conventional machine learning became quite powerful, it took 3 modern trends to bring about the emergence of deep learning. We'll talk about these 3 trends next. Now let's take a look at the trends that have helped us transition from conventional machine learning to modern deep learning. 3 trends have really driven the emergence of deep learning. We now have lots of data, we now have more powerful computers, and we've had several breakthroughs in machine learning algorithms in the past few decades. First, we now live in the era of big data. The amount of data that our world generates has grown at an exponential pace. In fact, the amount of digital information is doubling roughly every 2 years. This means that in the past 2 years, we've created more data than the entire history of the human race, and there doesn't seem to be any end to this trend in sight. For example, a modern jet engine contains roughly 5,000 sensors. Combined, these sensors generate a constant stream of data at a rate of 10 gigabytes per second for flights that are typically a few hours long. Now realize that there are over 100,000 flights a day, 365 days a year. It's pretty easy to see how these massive datasets can accumulate so fast. As a result, we now have vast amounts of data to train deep neural networks. And this is critical because deep neural networks require lots of data to train them effectively, much more data than conventional machine learning tools require. Second, we now have more powerful computers. We've seen a sustained exponential growth in the number of transistors per CPU for several decades now. Modern computers have much faster CPUs, more memory, and solid-state hard drives. In addition, we now have distributed computing technologies like Spark and Hadoop, which spread out data and processing over many computers. This allows us to train deep neural networks using clusters of computers rather than being confined to a single computer. This is also critical because it requires tremendous computational power to train deep neural networks, much more computational power than conventional machine learning tools require. Finally, we've had a series of breakthroughs in machine learning algorithms, many of which we discussed earlier in this course. These breakthroughs have significantly increased the power of neural networks. In addition, they've reduced the amount of time and the number of computations necessary to train progressively more powerful deep neural network models. For example, many deep learning algorithms have been rewritten to run on GPUs instead of CPUs. A GPU is the graphical processing unit in a computer, as opposed to the CPU, which is the central processing unit. These GPU-based algorithms typically afford orders of magnitude improvements in training time compared to their CPU-based counterparts. These are the same GPUs on the video graphics cards of modern desktop computers that make video game graphics look amazing. Coincidentally, the types of mathematical operations that neural networks require during their extensive training process are precisely those same operations that GPUs excel at. So, to be completely honest, we really have gamers to thank for some of the biggest advances in deep learning. However, this is just the beginning. We've already seen a lot of very impressive results from the first generation of deep learning algorithms. However, there are many more advances on the horizon that will significantly improve deep learning itself. For example, automated network design, model selection, and hyperparameter tuning to eliminate most of the time-consuming manual work involved in creating deep learning models. Transfer learning, where we update an existing deep learning model to solve a slightly different yet related task without having to retrain a new model from scratch. Alternatives to the current backpropagation algorithm, like the kickback algorithm, that may significantly reduce the training time for deep learning models. Alternatives to traditional neural network architecture, like capsule networks and modular networks, which may significantly reduce training time and further improve the power of deep learning. Evolutionary neural networks, where we use genetic algorithms to grow a custom neural network to solve a specific problem. Program synthesis, where we use deep learning to help write computer problems to solve new problems. Quantum deep learning, where we use quantum computers to radically improve model training time. And artificial general intelligence, the holy grail of deep learning, where we construct a machine intelligence that, in theory, can teach itself to solve any problem that a human can solve, and more. Some of these future deep learning trends are coming very soon, while others may be much further down the road if they ever appear. However, one thing I'm certain of is that deep learning is just getting started. There's a lot more that this technology has to offer, and I predict we'll be seeing tremendous advances in deep learning for years to come. So how is deep learning going to impact you, your organization, and our world? Deep learning is now being applied to solve problems in a variety of industries as well as many aspects of our personal lives. So let's take a look at a few examples. The place you'll most likely see a direct impact in the world of business is the area of knowledge work and decision making. Deep learning algorithms are beginning to outperform human decision makers in a variety of tasks. For example, sales forecasting, customer churn, product recommendations, and automated support. As a result, machines will likely augment or replace human decision makers in a variety of business tasks in the near future. Next, we have transportation and logistics. Deep reinforcement learning is currently being used to create self-driving automobiles. Over time, these vehicles will eventually replace all human drivers in automobiles, semis, boats, and airplanes. These autonomous vehicles currently have significantly lower rates of accidents, but can also drive without needing rest and will likely cost significantly less than human drivers. As a
Right
result,
now,
they
I
will
got a
not only
full health, so
revolutionize human
I'm gonna finish
transportation and
this
the
and then I'm gonna come
transportation of
back.
goods and services, but they will also likely revolutionize the insurance industry as well. Deep learning is also being applied successfully to robotics. This is allowing us to create general-purpose robots that can perform manual labor without being explicitly programmed to do so. You simply put the factory robot in training mode and grab its arm to show it how to perform a task. Then it will repeat the movements that you taught it to perform, compensating for variations with each new instance of the task it encounters, just like a human factory worker would do. The medical industry is likely to see major disruptions as deep learning begins to outperform human doctors in a variety of medical tasks. For example, in medical diagnostics, deep learning algorithms are becoming better than human doctors at detecting heart failure, traumatic brain injury, cancer, fractures, fetal distress, and predicting patient mortality rates. In addition, these machines now outperform human doctors in several areas of treatment as well. For example, tailoring treatment plans and prescription medications based on an individual patient's genetics in order to maximize the likelihood of success and minimize side effects. And for medical research, deep learning is being used to develop new pharmaceuticals and discover how genetic variations lead to certain diseases. Deep learning is about to make interacting with computers much easier as well. Deep learning is being used to create applications that incorporate anticipatory design, applications that are able to predict what task you're most likely intending to accomplish based on your previous interactions with the application. The application then provides you with a user interface best suited to complete that task. Deep learning is also enabling effective computing, computers with the ability to detect emotions in your face, voice, and words, read your lips, body language, and gestures, and understand the sentence structure, grammar, and context in your language. Essentially, this will enable much more natural interactions with computers. Deep learning is also playing a big part in creating smart buildings. These intelligent buildings can optimize their own energy efficiency, recognize the occupants of the building, respond to their commands, and anticipate their needs as well. This will have a huge impact on the functionality, efficiency, and security of commercial, industrial, and residential properties. In addition, this may likely have a huge impact on assisted living for senior citizens and disabled individuals. Deep learning is also enabling smart cities. It allows us to create intelligent cities that can optimize municipal resources like electricity, water, waste, and traffic without any human intervention. This has the potential to make entire cities more energy efficient, less wasteful, much safer, and operate more effectively. And this is just the tip of the iceberg. Almost every sector in our economy is beginning to see the impact of deep learning. For example, advertising companies to more effectively target their advertisements to consumers, the agricultural industry to improve farming efficiency, detect crop diseases, forecast commodity prices, and drive autonomous tractors. Educators to optimize teaching content, predict student achievement, and recommend education paths. The finance industry to trade stocks, price assets, detect fraud, approve loans, and design investment portfolios. Food service companies to automate ordering, food preparation, and delivery. Manufacturers to design new products, automate factory labor, and predict production demand and capacity. Media companies to recommend books, music, movies, and TV shows, target commercials to viewers, and predict the success of new content. And both online and physical retailers to recommend products, detect returning customers, and analyze in-store and website traffic patterns. Almost every industry you can imagine will likely be impacted by deep learning, since almost every industry has human decision makers in the middle of its processes, many of which can be augmented or automated by deep learning technologies. Any place in your business where a human is using data to make a decision may likely be affected by deep learning in the near future. In this module, first, we learned about the history of deep learning and the obstacles this technology has overcome. For example, we learned about the AI winter, which lasted from the late 70s to the early 2000s. Next, we learned about trends that are currently enabling and driving the importance of deep learning. For example, having lots of data, more powerful computers, and several breakthroughs in deep learning algorithms. Finally, we look to the future to see what impact deep learning will likely have on a variety of industries over the next few years. In the next module, we'll learn where to go to get started with deep learning. Hello again, and welcome to our final module on deep learning the big picture. I'm Matthew Renzi with Pluralsight, and in this module, we'll learn about next steps for getting started with deep learning. As an overview of this module, first, we'll learn about deep learning services, cloud-based APIs that you can call to solve common deep learning problems. Next, we'll learn about deep learning platforms, cloud-based solutions to solve specific deep learning problems. Then, we'll learn about deep learning frameworks, open source tools you can use to program your own deep learning solutions. Next, we'll learn about recommendations for which option to choose for each specific type of problem you're attempting to solve. Then, we'll learn where to go for more information on all of the topics in this course. Finally, we'll wrap things up for this module and for the course as a whole. So let's get started. So how do we get started if we want to use deep learning to solve problems in our organization? There are essentially three paths depending upon the type of problem you're attempting to solve. The three options are using existing deep learning services, using a deep learning platform to create and host a new deep learning model, and creating your own algorithm and model with deep learning frameworks. We'll start with the quickest, easiest, and least expensive of these options and work our way up to the most time-consuming, complex, and expensive option last. Our first option is using existing deep learning services. With deep learning services, a third party has created a training algorithm, provided the training data, and used their training algorithm with their training data to create a model that is hosted on their servers. So you can just call their API with your new data and use their existing model to make a decision or a prediction. There are a growing number of third-party deep learning service providers. For example, Google's Cloud AI services, Amazon's AI services on AWS, Microsoft Cognitive Services, and IBM Watson. These APIs allow developers to leverage existing deep learning models to add artificial intelligence to their own applications. Now let's take a look at a quick demo of how we could solve a difficult problem using an existing deep learning service. Imagine that we're building an application that needs to determine the age and gender of a person in an image. Within our application, we could make a call to Microsoft's face detection API within their Cognitive Services suite. First, we would send the image that we wanted to analyze to the face detection service using a web API call. However, for this demo, I'm just going to manually upload a photo of me to the web service directly. Next, the face detection service would feed our image into its deep learning model to analyze the image. Then, the web service provides us with the results of its analysis as a standard web response. Finally, our application would parse the results to extract the age and the gender of the subject. Please keep in mind that I'm demonstrating these steps manually through a demo interface to make things easier to understand for viewers without a background in software development. However, in reality, these operations would all be completed in code using a clearly defined and well-documented web API, the same type of API that developers use each day to build applications that talk to services in the cloud. So what are the pros and cons of using deep learning services? On the plus side, these services are simple. You just need to be able to call a standard web API to use them. They're quick to get up and running. It typically only takes a couple lines of code to integrate with one of these services. And they're inexpensive. Each transaction costs just fractions of a cent. On the downside, these services are generic. These deep learning models are designed to solve very common problems well, but they may not solve your specific problem in the way you need it solved. They're remote, which means you need to deal with complexities of distributed computing like fault tolerance and network latency. And they're pay-per-use. As your usage goes up, your costs go up as well. Ultimately, deep learning services work best to quickly solve common deep learning problems. Our second option is using a deep learning platform. With a deep learning platform, a third party provides a training algorithm, you provide the data, then you use your data with their algorithm to create a new model which they host in the cloud for you. There currently aren't many of these types of deep learning platforms that I'm aware of yet. However, I think this is a space that's going to explode in the next few years. Right now, there are only two platforms that I've used so far. First, Microsoft has a platform to train, test, and deploy deep neural networks using your own data via Azure Machine Learning. Second, Microsoft has two custom deep learning services, one for computer vision, where you can train it to recognize specific objects and images, and one for custom speech, where you can train it to recognize a custom vocabulary and speaking style. Now let's take a look at a quick demo of a deep learning platform. We'll learn how to use Microsoft's Custom Vision service for custom image recognition. More specifically, we'll use this service to perform facial recognition in order to detect photos of me versus photos of my friend and fellow Pluralsight author, Corey House. First, we start by uploading and tagging a series of photos containing both Corey and me. I've already uploaded a few images of us and tagged them with our respective names. As you can see, we have 6 images tagged Corey House and 6 images tagged Matthew Renzi. Next, we train a custom image classification model using each of these photos as training data and the tags we provided as training labels. As we can see, the service provides us with the precision and recall of the model it's created. Precision and recall are two measures in machine learning that tell us about a model's predictive power. The model appears to be performing well given the 12 images that we've trained it on. However, we could always increase the model's predictive power by providing it with more tagged images if we'd like. Once we've trained the model, we can feed it a new image and then it will predict who's in the photo. The service will return the name of the person and the likelihood that they are the subject contained in the photo. Even with only a handful of photos to train this model, the service does exceptionally well at predicting who's in each image. This is because the service is using a concept called transfer learning. It has already been trained extensively to detect a wide variety of images, so we're transferring that existing knowledge in order to solve a slightly different problem, that is, detecting specific people. Please keep in mind that once again, I'm doing everything by hand in this demo in order to keep things easy to understand. In the real world, you would need to write a program to communicate with this deep learning web service using its web API. So what are the pros and cons of using a deep learning platform? On the plus side, these platforms are still relatively simple. You provide labeled training data and press a button to build the model. Then you can call an API with new data to get your prediction. They're relatively quick, Once you have a training dataset, you can train one of these models in just a few minutes to a few hours, depending upon the complexity of the model. And they're relatively inexpensive. The cost of training time and the transaction costs are still quite reasonable. On the downside, these platforms require training. You need to provide the platform with a training dataset to teach it to make predictions. They're remote, you still need to deal with aspects of distributed computing like fault tolerance and network latency. And they're pay per use. You're now paying for both training time and per transaction usage. Ultimately, deep learning platforms work best for custom scenarios where you want to use someone else's algorithm, but you need to use your own data. Our third option is to use a deep learning framework. With a deep learning framework, you create the training algorithm, you provide the data, then you use your algorithm and your data to create your own custom model that you can host yourself. However, this means that you need to code everything yourself as well. Fortunately for us, we now have really good free open source deep learning frameworks that allow anyone to create your own deep learning algorithms. For example, Google's TensorFlow, which supports Python, R, and C++, and is currently the most popular of these frameworks. Microsoft Cognitive Toolkit, which is highly optimized and provides support for Python, C++, and C#. Keras, which sits on top of TensorFlow to make it much easier to use. Torch, which is a Lua-based framework used by Facebook, Twitter, and Google. MXNet by Apache, which provides support for R, Python, C++, and Julia. And Caffe and its successor Caffe 2, which provides support for both Python and C++. Now let's take a look at a quick demo where we'll create a deep neural network using the Keras and TensorFlow frameworks. In this demo, we'll construct a convolutional neural network that can classify handwritten digits. We'll be using the programming language Python with the Keras framework, which is a high-level API that sits on top of TensorFlow. We're just going to focus on the code that constructs the deep neural network and skip over all of the code that loads the data and prepares it for training. Also, please note that this demo is just to give you an idea of what programming with deep learning frameworks looks like. It's not to teach you in depth how to use Keras or TensorFlow. First, we start with a sequential model, which allows us to describe a deep neural network model as a sequence of connected layers. Next, we specify we want our first layer to be a two-dimensional convolution layer with 20 filters using a 5x5 kernel. The input shape of our data is the original 28 by 28 pixel image of each handwritten digit using a single grayscale color channel. Next, we'll add a rectified linear unit or ReLU activation function to our convolution layer. Then we'll add a pooling layer using a 2x2 max pool with a stride of 2. Next, we'll add a second convolution layer with 50 filters using a 5x5 kernel, followed by another ReLU activation function, then a second 2x2 max pooling layer. Next, we'll flatten this 3-dimensional layer of neurons into a 1-dimensional layer of neurons. Then we'll add a fully connected hidden layer with 500 neurons, followed by another ReLU activation function. Finally, we'll add our output layer, which is a fully connected layer with 10 output neurons, 1 neuron for each of the 10 possible digits being classified. We'll use a softmax activation function on this final output layer, which is an activation function commonly used for classification. With our deep convolutional neural network defined, we can compile this model specifying a loss function, an optimizer, and a metric to optimize. Then we train the model specifying our training data, which is our handwritten digit images, the training labels, which are our correct answers, the batch size, and the number of training iterations. We then wait for the training process to complete, which for the sake of time, we'll just skip over. Finally, once our model has been trained, we can evaluate the model's performance using the test data and the test labels. As we can see, our model is able to detect handwritten digits with approximately 98% accuracy. Now we can feed new data into our model and it will predict which digit it's seeing. So what are the pros and cons of using a deep learning framework? On the plus side, these services are custom. You can train your model with your own data and tune it exactly how you like it. They're local, you can host your model on premises, in the cloud, or embed your model right into your application. And they're private. If you have sensitive customer data or you're creating proprietary technology, neither ever has to leave your data center. On the downside, this option is complex. Building algorithms, preparing data, and training deep learning models requires a lot of knowledge and skill. They're labor intensive, it takes a lot of time to create the algorithms, gather and prepare the data, and train the model. And they're expensive. The amount of time and effort required makes this by far the most costly of these three options. However, sometimes the problem you're attempting to solve can only be solved with this option. Ultimately, you should use this option when neither of the first two options are possible. If you're still not sure where to begin, I'd like to give you a few recommendations. My hope is that this information will help you decide which deep learning option is right for the problem you're trying to solve. First, I think it's very important to point out that many modern machine learning problems can be solved without deep learning. Deep learning is great for modeling complex functions like all of the examples we've seen in this course. However, many business problems involve functions that are simple enough that they don't require machine learning. So be sure you've exhausted all of your traditional machine learning options before you make a significant investment in deep learning. Second, use existing deep learning services for common, well-defined use cases. These are typically common problems that have already been solved many times by deep learning service providers. For example, basic image recognition, speech recognition, and sentiment analysis. Third, use deep learning platforms for custom one-off use cases. These are typically problems that are similar to problems someone else has already solved, but different enough that the existing solutions won't work for your needs. For example, training a model with your company's own data, detecting your company's logo and social media photos, and speech recognition for domain-specific vocabulary. Fourth, use deep learning frameworks to build your own deep learning solutions when neither the existing services nor existing platforms are able to solve your problem. These are typically problems that no one else has solved yet, or your solution is unique enough that you can't use an existing solution. For example, you're building a brand new model that no one else has ever built before, you have sensitive data that can't be moved to the cloud, or the transaction cost would be too high at scale to use a third-party cloud service provider. And finally, I recommend that you use the simplest tool that effectively solves each problem you're attempting to solve. Deep learning is complex enough, so there's no need to add unnecessary complexity if there's a much simpler solution available. So where do we go from here? How do we learn how to use deep learning to solve problems in our organization? First, there are several courses on Pluralsight that will take you much further with deep learning and more generally, data science, machine learning, and artificial intelligence. If you're interested in using TensorFlow to create deep neural networks, start with TensorFlow Getting Started. If you're interested in learning more about machine learning in general, I recommend Understanding Machine Learning. If you're interested in learning more about data science in general, I recommend my course Data Science: The Big Picture. Finally, if you'd like to get more hands-on, I recommend my course Data Science with R. This course will walk you through the data science process, including machine learning using R, which is one of the top programming languages for data science and machine learning. However, new courses are being added to Pluralsight every day, so please be sure to check out all of my new courses at the URL at the bottom of the screen. Next, be sure to use me and my website as a resource too. I have tons of learning resources available, including articles, videos, presentations, and open source software covering this topic and more. Finally, before we wrap things up for this course, feedback is very important to me. I use your feedback to improve each and every one of my courses, so please be sure to take a moment to rate this course, ask questions in the discussion board if there's something in this course that you didn't understand or would like me to clarify, leave comments to let me know what you found valuable about this course or if you think there's something I could improve upon for future courses, and feel free to send me a tweet on Twitter if you'd like to provide me with feedback in public. My Twitter handle is @MatthewRenzi. In this course, first, we learned about deep learning, what it is, how it works, and why it's important. Next, we learned about techniques used to enable deep learning, including fully connected neural networks, convolutional neural networks, recurrent neural networks, generative adversarial networks, and reinforcement learning. Then we learned about applications for deep learning, including applications for tabular data, text, images, audio, video, and more. Next, we learned about the impact of deep learning technologies. We learned about the history of deep learning, the trends driving deep learning, and the industries that will most likely be impacted by deep learning in the years to come. Finally, we learned about how to get started with deep learning. We learned about 3 options for getting started, including deep learning services, deep learning platforms, deep learning frameworks, and where to go next for more information. Thank you for joining me for this course on deep learning. I hope that you've learned some valuable information that you'll be able to put to great use. And I hope to see you again in another Pluralsight course in the future. Hello again, and Hi, I'm Matthew Renzi with Pluralsight, and welcome to Data Science: The Big Picture. Data science is the practice of transforming raw data into actionable insight. In our data-driven economy, this set of skills is in extremely high demand and commanding significant increases in salary as it's revolutionizing the world around us. However, most developers and IT professionals have not yet learned this valuable set of skills. In this course, we'll answer the following 3 questions. What is data science? Why is it important? And where is this all going? To answer these questions, we'll look at a series of trends that are driving the data science revolution, including data analytics, the Internet of Things, big data, and machine learning. Finally, we'll see how all these trends are converging to create fully autonomous, intelligent systems which will likely revolutionize our economy and our world as we know it. By the end of this course, you'll understand data science and the tools, technology, and trends driving the data science revolution. As an introductory course, there are no prerequisites for this course. We'll be explaining everything you need to know along the way. So please join us today at Pluralsight and learn how to become part of the data science revolution with Data Science: The Big Picture. Hello, and welcome to Data Science: The Big Picture. I'm Matthew Renzi with Pluralsight, and in this course we'll learn about data science from a high-level perspective. Whether you realize it or not, there's a flood of data coming. In fact, the flood is already here, and it's growing exponentially each year. In the next few years, we're going to see 2 entirely different outcomes for individuals, businesses, and governments based on whether they learn to use these data to their advantage or not. Either these people, businesses, and governments are going to sink in the coming sea of data, or they're going to learn how to swim. So I'm currently doing what I can in my professional career to learn how to swim in this new data-driven economy, and I encourage you to do the same. We see the same sentiment expressed by experts across various industries. In fact, I see articles like these popping up on a daily basis. There really seems to be something big happening in the world of data and data science. The reality is that there's a rapidly growing demand for IT professionals with the ability to transform data into actionable insight. However, there are nowhere near enough people available with the proper skills and tools to meet this demand. This means that people with the right set of skills and the right tools are commanding significantly higher salaries in the IT industry right now. And those of us with data science skills are going to be leading the software industry through the next industrial revolution, an information revolution. So you might be thinking to yourself, I'm not a data scientist, a data analyst, or data engineer, so how does data science apply to me? The reality is that as a software developer, a data professional, or an IT professional, you work with data every day, and you can learn to apply data science practices to your data to identify patterns, to make better decisions, and to predict outcomes. In fact, if your job doesn't involve working with data, it's likely that it may not exist in a few years. As we'll soon see, data science is automating the world around us. So I'm very happy that you decided to learn more about this topic, and I'm excited to teach you a bit of what I know about data science. As an overview of this course, first we'll learn about data science, what it is and why it's important. Next, we'll learn about data analytics, the application of data science in the business world. Then we'll learn about the Internet of Things and how connecting devices and sensors to the cloud provides us with a tremendous stream of data to be analyzed. Next, we'll learn about big data and how to effectively store and process massive amounts of data. Then we'll learn about machine learning, software able to detect patterns, make decisions, and predict outcomes using data without explicitly being programmed to do so. Finally, we'll close the loop to show how all of these data science trends are converging to create fully autonomous systems that behave rationally in their environment and learn without any human intervention. So let's get started. The purpose of this course is to address the following 3 questions. What is data science? Why is it important? And where is this all going? In addition, by the end of this course, I'm hoping that you'll be as excited as I am about the future of data science and what it means for those of us in the software industry. The intended audience for this course are software developers, data professionals, and IT professionals. This content is applicable to a wide audience including novices just starting out in the software industry and wanting to understand how data science will affect your career, all the way up to managers and executives wanting to understand how data science will impact your business. Essentially, this course is for anyone in the IT industry who wants to understand what data science is, why it's so important to our industry, and what direction these trends are moving. Since this is an introductory course, there are no required prerequisites. However, I do want to point out that this course is intended to be a very high-level introduction to data science. We will not be seeing any code demos or performing hands-on data science work in this course. If you're looking for a more in-depth hands-on course, please watch my Pluralsight course on data science with R. This course covers how to perform basic data science practices using R, which is one of the most popular programming languages for data science. However, I would still recommend that you start with this course first and then move on to that course next for more in-depth hands-on knowledge. You can find this course at the following URL. So now let's learn what data science is and why it's so important. Now let's learn about data science, what it is and why it's important. The first question we need to answer is, what is data science? Data science is an interdisciplinary field composed of computer science, math and statistics, and domain expertise that seeks to derive insight from data. Data science is the intersection of these 3 respective disciplines. The goal of data science is to transform data into knowledge that can be used to make rational decisions. So what then is a data scientist? A data scientist is someone that performs data science for a living. However, a data scientist is more than just a scientist, more than just a data analyst, and more than just a developer. They possess all three sets of skills. Individuals with all three sets of skills and proper credentials are currently very rare. The next question we need to address is what set of skills are necessary for data science? In general, the skills commonly associated with data science are programming computers using programming languages like SQL, Python, and R, working with data, that is collecting, cleaning, and transforming data, creating and interpreting descriptive statistics, that is numerically analyzing data, creating and interpreting data visualizations, that is visually analyzing data, creating statistical models and using them for statistical inference, hypothesis testing, and prediction, handling big data, that is data sets that are too large to work with by a conventional computing architecture, automating decision-making and prediction using machine learning algorithms, and deploying data science solutions into production to communicate results to a wider audience. So what tools are used to perform data science? To answer this question, here's a chart of the top programming languages currently in use today. On the x-axis, we have the percent of respondents reporting that they use the corresponding tool. On the y-axis, we have the name of the programming language. Python is currently the most popular language for data science. It's free, open source, very powerful, and works well for a variety of tasks. Next, we have R. R was created specifically for statistical data analysis, so it works very well for many data science tasks. Third, we have SQL, also known as structured query language. SQL is the most popular language for querying databases, so it's commonly used in many data science workflows. And I should note that all three of these languages each have their own pros and cons, so I recommend that you learn all three and then use whichever tool is best suited for each specific task. Next, we have desktop applications used for data science. Excel is by far the most popular. It's well known, easy to use, and works well for basic data analysis. Tableau is a popular data visualization tool. It allows you to create various dashboards and data visualizations using a drag-and-drop user interface. Weka is a desktop application for training machine learning models, which is very simple and easy to use. All of these desktop applications are considered low-code and no-code tools, which makes them ideal for many users. For big data platforms, we have Spark, which is an open-source distributed database. Spark has become popular because of its scalability, performance, ease of use, and open-source license. Hadoop is an older distributed database technology similar to Spark. There are a variety of open source and commercial products built on top of Hadoop. And Kafka is an open source distributed data stream processing platform. It focuses on data in motion rather than data at rest. Finally, we have data science platforms. RapidMiner allows users to build data science workflows using a drag-and-drop interface with little to no programming. Microsoft Power BI allows users to build reports, dashboards, and data visualizations using low-code and no-code tools. And KNIME is very similar to RapidMiner in that it allows you to build data science workflows with little to no code. Data science platforms are evolving quickly, so up-and-coming tools like Databricks are quickly growing in popularity. Finally, we need to address the question, how is data science performed? The general data science process works like this. First, we find a question that we want to answer. This can be a hypothesis we want to test, a decision we want to make, or something we want to attempt to predict. Second, we collect data for our analysis. Sometimes this means designing an experiment to create new data. Other times, the data already exist and we just need to find them. Third, we prepare the data for analysis, a process often referred to as data munging or data wrangling. We need to clean and transform these data to get them into a form suitable for analysis. Fourth, we create a model for our data. In the most generic sense, this can be a numerical model, a visual model, a statistical model, or a machine learning model. We use this model to provide evidence for or against our hypothesis, to help us make a decision, or to predict an outcome. Fifth, we evaluate the model. We need to determine if our model answers our question, helps us make a decision, or creates an accurate prediction. In addition, we need to make sure that our model is appropriate given our data in the context. Finally, if everything looks good, we deploy our model. This could mean communicating the results of our analysis to others, making a decision and acting upon our decision, or deploying an application into production. We then repeat this process for each question we would like to answer using feedback from our previous results to help guide our process. Data science is typically we then repeat our model. This could mean communicating the results of our analysis to others, making a decision and acting upon our decision, or deploying an application into production. We then repeat this process for each question we would like to answer using feedback from our previous results to help guide our process. Data science is typically an iterative process. We typically go through the complete cycle multiple times, learning and improving with each iteration. In addition, this process is often non-sequential. We often have to bounce back and forth between steps as we discover problems and learn better ways of solving these problems. In addition, there are times when we don't need to complete the process. Often, we learn that what we're doing isn't working or doesn't make sense given our data or context, so we terminate the process and shift our focus to the next most important question in our to-do list instead. There are some well-established practices for the data science process available, like the CRISP-DM process, which stands for Cross-Industry Standard Process for Data Mining. These established processes are useful to help you get started with your data science process. So now, let's learn why data science has become so important in recent years. So why has data science become so important all of a sudden? To answer this question, we need to look at a series of emerging trends that are driving the importance of data science. First, we'll learn about data analytics, the trend of applying data science practices and tools in the business world. Second, we'll learn about the Internet of Things, the trend of connecting devices and sensors via the cloud, which is generating massive streams of data to be analyzed. Third, we'll learn about big data, a trend of creating tools and systems able to store and process these enormous data sets at scale. Fourth, we'll learn about machine learning, a trend in artificial intelligence of teaching machines to solve problems without explicitly being programmed to do so. Machines able to make decisions and predictions, all by identifying statistical patterns in these massive data sets. Finally, we'll close this loop to show how all four of these trends are converging to create fully autonomous intelligent systems, machines capable of acting rationally within their environment and learning how to optimize their performance over time without any human intervention. For each of our four main topics, we'll learn about trends within each topic that have been occurring over the past few decades. We'll also learn where these trends currently are at today, and we'll try to predict where these trends appear to be going in the next decade or so. Ultimately, the importance of data science all boils down to two things. It's being driven by economics, and it's being made possible by technology. The cost of collecting, storing, processing, and analyzing data is continuously decreasing, and the value that these data can provide when the data science process is applied continues to increase. As a result, data science has now become a cost-effective strategy for answering questions, making decisions, and predicting outcomes in a wide variety of scenarios in our world. Given this trend, it's unlikely that the demand for data science will decrease anytime in the near future. So now, let's wrap things up for this module so that we can get started learning about the various trends driving the importance of data science. In this module, first, we learn what data science is. We learn that the goal of data science is to transform data into knowledge that can be used to make rational decisions. Then we learn about the skills that are important for data science, the tools that are used, and the data science process. Finally, we provided a basic argument for why data science has become so important in recent years. The remainder of this course will examine this more in depth by looking at each of the four key data science trends and discuss where these trends appear to be going in the future. In the next module, we'll learn about data analytics, the application of data science practices to the world of business. Hello again, and welcome to our next module on data science, the big picture. I'm Matthew Renzi with Pluralsight, and in this module, we'll learn about data analytics, the application of data science practices to the world of business. As an overview of this module, first, we'll learn about data analysis, the predecessor to data analytics and the core of data science. Next, we'll learn about data analytics, the application of data science practices to the world of business. Then, we'll learn about data-driven decision-making, the future trend of data science in the business world. Finally, we'll see a few examples of industries that have been significantly disrupted by the application of data science to their professions. So let's get started. First, let's take a step back into the past, a few decades ago, to discuss data analysis, the predecessor to data analytics. Just a few decades ago, data analysis was largely the domain of two kinds of people: scientists doing research in fields like physics, chemistry, and economics, and statisticians, which were a bit of a rarity in the business world, and when you found them, were typically found in industries like insurance and finance. Back then, testing a hypothesis with data wasn't easy. We had to design an experiment, run the experiment, collect data, and then analyze the data to provide evidence for or against our hypothesis. This took significant time, money, and effort. To analyze the data, we had complex proprietary software. These tools were expensive, took a long time to learn, and required a deep understanding of statistics in order to use them properly. To communicate our findings, we typically used numerical reports, clunky data visualizations, and scientific articles. Communicating insight to a wider audience was costly, often ineffective, and relatively slow. Ultimately, in the past, collecting, analyzing, and communicating data was difficult, expensive, and slow. So now, let's look to the present to learn about data analytics, the adoption of data science practices in the world of business. Now let's learn about data analytics, the application of data science practices to the world of business. Today, the marketing departments of the world have renamed data analysis to the much flashier term data analytics. However, despite the flashy new title, data analytics is still good old-fashioned data analysis at the core, but it's improved in several ways. Most importantly, it's spread from the domain of science to the world of business as well. This means that it's now widely acceptable to use data analysis in a scientific method to solve common business problems. In addition, data are now inexpensive and readily available. We can run an A/B test on a website with a simple flip of a feature toggle. This means that we can collect data easily and with significantly less cost. In fact, oftentimes, we don't even need to run an experiment to collect data. The data already exist, we just need to find them and analyze them. We have much better tools for performing data analysis as well. We now have easy-to-use spreadsheet software like Microsoft Excel for performing numerical analysis. We can also create interactive charts and graphs using software like Tableau, which makes creating data visualizations relatively quick and easy. And we have open-source programming languages like R and Python that make more rigorous data analysis inexpensive and relatively easy as well. We also have a variety of ways to communicate our findings to others. For example, we can convey key performance indicators of our business to executives, management, and employees using dashboards. In addition, we can convey complex information about our business to a wider audience using infographics that allow users to rapidly consume and digest data. Ultimately, today, collecting, analyzing, and communicating data is easy, inexpensive, and fast. So now let's look to the future to see the direction of trends driving data science in the world of business. So what will the future of data analytics look like? Current trends indicate that we're moving towards a world of data-driven decision making, an age when all non-trivial business decisions will be made using data rather than guesswork or gut instinct. In the future, we won't have to spend time collecting data like we did in the past. We'll have almost all the data we need right at our fingertips. This trend is being referred to as the democratization of data. In the business world, this means that employees will have access to significantly more of their company's data. Data isn't just for managers and executives anymore. This means that anyone in the company can run an experiment to test a hypothesis and use data to drive their own decision making. In addition, we see this happening in the public sector with open data initiatives. Governments are opening up their previously private datasets, and scientific research datasets are being made public as well. We're also seeing this trend emerge in our personal lives. We have devices like fitness trackers and sleep trackers that allow us to optimize our daily lifestyles, and crowdsourced initiatives involving personal health data that help people with medication, side effects, and managing symptoms. In addition, we have a new generation of tools that will allow almost anyone to perform their own complex data analyses. We'll have self-service business intelligence tools that allow almost any employee to analyze their organization's data. We'll also have natural language query applications that allow you to speak a question and receive an answer based on your organization's data. Similar to how Amazon Alexa or Apple's Siri work, however, you'll be asking questions about your own business using your company's own data. To communicate information, we'll have new tools that allow us to tell better stories with our data. For example, interactive and immersive data visualization applications using augmented reality and virtual reality. Imagine putting on a HoloLens or an Oculus Rift and being able to immerse yourself within your own company's data. This is leading to the data-driven enterprise, companies that value information as an asset and use data to drive their decision-making. Initial findings from MIT research show that companies that are implementing data-driven decision-making practices had 4% higher productivity and 6% higher profits than traditional businesses. In the highly competitive landscape of the future, companies that are not data-driven may eventually cease to exist. As a result, it's important to ask yourself if your organization is on the road to becoming a data-driven enterprise, and if not, what can you do to help it make better decisions using data? However, empowering people to make better decisions is not the end goal of data science. Rather, as we'll soon see, it's just the beginning. So now, let's take a look at a few examples of industries that have been disrupted by the introduction of data science into their professions. Before we wrap up this module, let's take a look at 3 examples of industries that have been completely disrupted by data science. I think it's important to see some real-world examples of how data science is changing the world of business in order to anticipate the impact that data science may likely have on your industry. First, the financial industry. Just a couple decades ago, the trading floors of Wall Street and other exchange markets were filled with people yelling and screaming to buy or sell stocks, bonds, and other securities. At the intersection of every trade were people using a combination of information, guesswork, and gut instinct to make trading decisions. However, trading room floors are mostly empty these days. Stock trading shifted from human interactions on the trading floor to quantitative analysts sitting behind computer screens in backroom offices. Quantitative analysts, or quants as they're simply known, use data science to scientifically investigate investment hypotheses and build models to predict investment outcomes. In recent years, however, even quants have replaced themselves with automated intelligent trading algorithms. Today, lightning-fast, high-frequency trading algorithms now account for the majority of all trades in the modern stock market. As a result, Wall Street has been forever changed by data science. Second, we have baseball. Prior to 2002, picking a lineup of players in the Major League Baseball draft largely relied on traditional measures of player performance, like stolen bases, runs batted in, and batting average. In addition, the scouting profession was full of human biases that distorted the true value that each player brought to a baseball team. However, in 2002, the Oakland Athletics baseball team used data science to select players that were undervalued by the market. Through rigorous statistical analysis, the Oakland A's discovered that metrics like on-base percentage and slugging percentage were better indicators of offensive success. Despite their significantly smaller budget for player salaries, the Oakland A's created a team that was competitive against the much better funded teams. This data-driven strategy contributed to the Oakland A's setting a record 20 consecutive wins and brought them to the playoffs in 2002 and 2003. As a result, the game of baseball and how players are valued has also been forever changed by data science. Finally, the insurance industry. The insurance industry was an early adopter of the use of data and statistics in the business world. These early data science practices were used to calculate the aggregate risk of groups of